Okay, in this lecture we're going to go through initial discussion on Chapter 7, which is computer implementation. And the basic question is, remember that we have this matrix equation. And to get this matrix equation, what we've done in the past is we've set up this integral equation. It's based on derivatives of our interpolation functions. And then we integrate this by hand explicitly, and we can get a set of equations. It's very difficult to tell a computer to do a symbolic integration, particularly on a complex domain where your finite elements may be of varying size. Remember, we have this length HE. We normalize it, but you may want to have certain elements that are very refined. If you have field or stress concentrations, other places you may not want a very refined mesh. Because remember, when you make the mesh refined, you've got to add up all these elements. So your matrix, your K matrix, becomes extremely large. So the big question is, how does the computer handle this integration? Since we really don't want to go through an analytic integration. So you have to go back and think about your numerical methods class. Right, so before we jump straight into engineering ODEs, just think about if you have some function of x and you want to integrate it from xa to xb. And as an example, you can say this is from over one single finite element, from xa to xb. Well, when we put this on a computer, now we're not going to get an analytic solution, so we're going to approximate it and hope that our approximation is close to this. So instead of doing an explicit continuous integration, we're going to do a summation. So what we're saying is we have some polynomial and we have these constants here, and hopefully we can find a combination of these constants and this function that give us a good approximation. So consider this function psi of polynomial degree n minus 1, and then this function fi. These are values of the true function at discrete points x of I. That's somewhere over this domain from xa to xb. Alright, so let's just consider a simple case where if you have n equals 2. So you probably remember, or should remember from numerical methods, that it turns out when n equals 2 in this formulation, this is trapezoid rule. So if you have some curve here, you have xa and xb, here's our f1, f2, take a linear interpolation. Now the area under this trapezoid is how we're approximating the integral. So if v1 is given by here, or if v2 is given by this, h is the length, then that's it. So this is essentially an example of numerical quadrature. So this true integral is being approximated by the evaluation of the function at discrete points times a weight function we're calling w sub I. So here are your quadrature points, and these are your quadrature weights. So you'll hear me talk a lot about numerical quadrature. What I mean is we're doing this numerical integration. Now the most common is Gauss-Legendre, and what we do in this case, very important here, is a coordinate transformation. So we go from our true coordinates x, so this is on a physical domain of a system that you can go into the laboratory and measure, and then we're going to convert this to a normalized domain from -1 to 1. So here we have x sub a. We're going to c is -1 at xb. C is 1. To do this transformation, you simply write your true coordinates in terms of the normalized c coordinates, and here's that relation. And you can check this. You plug in plus or minus c, you'll find this is either xa or xb, where he is the element length. Alright, so interpolation functions. So in this problem, our interpolation functions are given by this form. So these are analogous to the interpolation functions that we use in Galerkin method. So these are just linear interpolation functions. They're 0 or 1 on the endpoints. Alright, so we have this, and we define C in the middle of this domain, plus or minus 1 on the ends. Alright, so we're not completely done with this transformation. There's a few other things to consider. So we have x here, so if I just call x as a function of c, we've already introduced the explicit relation. In general, we could define, instead of writing this out, we could just define it as a summation. So you have these quadrature points and this function psi sub I, where these are my global coordinates x sub I. And the notation often used in Ready and other textbooks is this integration in the true domain from x of a to x of b is converted to this local unitless or unit normalized coordinate from -1 to 1, where we're calling this function f sub hat, since it's related to this, but we're working on a different coordinate system. These are equal based on this relation. And the other important thing here is we've converted this function from x to c, but we also have dx and dc. So dx is a function of c, so you have to take this derivative times dc, where that derivative is we call j, or Jacobian. So in summary, the most common form that we use is called an isoparametric formulation. In that case, your solution is approximated by a number of interpolation functions, j1 to n. So far in these 1D problems we've typically focused on n being 2, but remember, this is the solution of, say, your displacements or temperature or whatever the physics of the problem is. This is your coordinates, so we're doing an additional interpolation on these coordinates, and if you use the same approximation of your integral, here it's I 1 to m, here j 1 to n. If m equals n, then you have an isoparametric formulation.